Hey guys. Today there's the CodeCraft 21 and also the Codeforces Round 7-11. As always, I'm never prepared at the beginning, so I guess we're gonna have fun with that. And one final thing, I said I would start a new style of like explanations where I would do like a quick thing and then later on I would go into a more detailed thing so that like you can, if you just want like a brief overview, you can have that, and if you want the full solution, you can have that as well. Hopefully I remember to do that. If so, the timestamps will reflect it. If not, I guess I just won't. I don't know. I'll try my best. Yeah. Update the sub count. I think we're good. Let's do this. The GCD sum of a positive integer is the GCD of that integer with its sum of digits. And the smallest integer such that GCD sum of x is greater than 1. Okay, so any single digit will work. So any uniform number of digits. Like if I have 5 2s. Yeah. Let's see. Okay. So the important thing here is that any multiple of 3 is like you know the common thing where any multiple of 3 has the sum of its digits also has a multiple of 3. I don't know where my pen went, but don't think I guess I don't need it for this, but I will need it later, so that's a bit concerning. But basically any multiple of 3 will work. So basically like we'll find it within 3 iterations if we do brute force, because it will always work for a multiple of 3. So x is greater than 0. So we basically just implement sum of digits. So read in test cases, c into n, while 1 if n is greater than 1. There we go. So you might even accidentally solve this problem just because the brute force will work so quickly. Yeah. Seems good. I have to use the M sites, I guess that's fine, if necessary. As always, I'm a bit late, so we're slightly behind, but it's fine. Alright, box fitting. You're given n rectangles of height 1. Each rectangle's width is a power of 2, okay? Given a 2-dimensional box of width W. Smallest height of this box such that it is able to fit all the given rectangles. Interesting. So I guess we want to pack our rectangles like as efficiently as possible. Alright, definitely need my pen for this, so I don't know where it is. Always somehow manage to lose this, like every time. Like seriously, what is up with this? Oh. Okay. Always left it in a place where I wouldn't have expected it. Okay, so Can we assign them greedily? I guess because they're powers of 2, we can. It's kind of like coin change, where the greedy for coin change will always work because everything else is a multiple of the other. So like, yeah, you can't like. So the reason powers of 2 are nice is because greedy works, because like every box is always going to be a multiple of every other smaller box. So what that means is that like, wait, these are supposed to be even. So that means like there's no way to have like 3 of these boxes, for example, and take up like, for example, 9 space so that you could I don't know what I'm saying. It's like coin change basically, I guess. Like there's no way to how do I describe this? I don't know, I guess I'll try and prove this later. I still haven't fully woken up because I'm like always tired or something now, so I will worry about this later. So basically, I'll count. Basically, like, say you choose at least 2 smaller boxes, then you might as well have chosen the larger one because it'll give you more freedom in the future to have the smaller ones ready than if you had the larger one. I guess that's the idea basically. So there's never any reason to like take 2 smaller ones over a bigger one. Each WI is a power of 2. So we look at the largest power of 2 first. I guess we can say like that's equivalent to dividing by 2, I think. While oh wait, actually this should be that. Make this like 3 million or something. While W. So basically just gonna take a current, like a single layer, and then greedily assign things to that layer. So while count I is greater than 0 and cur is greater than or equal to I, so while we can fit it and while we have more, minus minus count I, minus n, and cur minus equals I. Then each of these is another layer we have to have. Oh my god, cannot type. Great. Oh wait, what did I do? What the hell was that for? Also, this assures that count is reset after every test case. Yeah, seems good. We actually don't need to iterate over this one, but it barely makes a difference. So this should be theoretically log per element, so it's like n log n something. N log a million. Should be good. Cool. Alright. Gowring is grown up in a mystical universe. Sorry for my pronunciation in advance. He's grown up in a mystical universe. He is faced by n consecutive 2D planes. He shoots a particle of decay k. What? A particle can pass through a plane directly. However, every plane produces an identical copy of the particle going in the opposite direction. Oh. Okay. Right. So it goes like that, then it produces that, then it produces that, etc. That's... Okay. So we have to find the size. So that's mathy. Okay. So how many... All test cases in one test are different. That doesn't seem to make a difference. So like if we do this, I guess we have to solve it in O of nk. So like for the first step, it'll touch it at all of these exactly once. And then for the second step, like we'll create something here and that'll touch all of these, and then we'll create something here and that'll touch all of these, and then we'll create something here and that'll touch all of these, and so on. And I guess we can do like prefix sums or something. So we can basically like say we're gonna reverse everything and that'll make prefix sums or something. And then now we have like 6 over here, and we have 5 over here, and we have 4 over here. And all of these 6 are gonna go this way now, and all of these 5 are gonna go this way now, and etc. Does this have a large test? Oh, it does. Okay. Nice. So they do have something. And so I guess we're just going to do prefix sums a lot of times, because this 6 is now going to affect all of these. Yeah, basically it's prefix sums. I guess that's the idea. That's not that fun. So now we make a count of 1005 modulo 10 to the 9th plus 7. So actually, what's k? Oh, right, okay. C into n to k. Lance equals 1. So k times so actually it might help to do like count 0 is equal to 1. Is it 0 or n minus 1? It should be the starting point, and then that will touch everything. Then we assume they'll go that. Okay, now alright, this should be up to k. 4. This should be up to n. R is equal to r plus count I. Mod. Count I is equal to r. Then we reverse it. And the reversal basically makes it so because it like goes in, it goes like left and then right and then left and then right, then it becomes like not a problem. Okay, that is a problem though. 6641. That makes even less sense. Wait, what? We have n planes. Why are there 2 here? Oh. Oh, right, okay, so this is like, also this should be J, not I. So we definitely add the answer. And then that will affect everything, my bad. So it affects everything, yeah, so count I is equal to R. Yeah, okay. Because it doesn't affect the column we're at, it will only affect the columns like to the right of it and stuff. So I guess it doesn't make the most sense. I might get that. Okay, great. What's with that? Something's messed up. There's like a slight off by 1 error going on here, but there's something else too. So 1, 2, 3. Why does it become 0 instantly? Oh, duh. Alright, we can't both replace and do that at the same time. There's a slide off by 1 error here. Okay, that's annoying. So 10, 10, 10. What does that break then? Like it's 3, 2, 1, and 1. It's just like consistently off by 1 or something. Yeah, it's almost consistently off by 1. That's stupid. I think is it because I'm not counting the right one? Oh, wait. How does this work? So I know if I have k equals 1, it's going to be like wrong in a lot of places. So it should be like off by 1 everywhere except for when k equals 1. So if k is greater than 1, like add 1 to answer something. I mean, it works. Answer should be 1 there. Yeah. 1, 19, 2. Answer should be 20. So why does it get that wrong? I guess it's because it doesn't consider what happens first. Oh yeah, wait. If I did this... no, I think I can just take this as a special case. Yeah, it's just a special case. Okay. I trust the code. It passes the huge test, so it's probably fine. Oh no, I might get wrong answer for this. If I do, screw it. Wait, constraints are up to 1,000. It's NK. Should be good. Might get hacked or something, but should theoretically be good. They do have multitests everywhere. Okay. Alright, bananas in a microwave. So looks like it has that kind of like interactive feel to it, but it's not interactive. So that's weird. How's this doing? How are we doing? Alright, decent speed, pretty good. Rainboy has F in 16 minutes. So maybe this is going to be one of those easy contests. Maybe it will be. Alright, you have n time steps before the microwave stops working completely, and each time step it displays a new operation. Let k be the number of bananas in the microwave currently. The ith operation, you're given 3 parameters. Wait, what? N time steps. Oh, so you want to create exactly j bananas. Alright, pick an AI and add some multiple of xi, or multiply it by some power of xi. Xi can be a fractional value. Can it be negative? Oh, it's ceilinged. What? 10 to the 5th. What? Alright, this makes a lot of sense. And I guess it's like doing BFS. So for the first thing, we can do some sort of like prefix sums or something. We can round xi down and then it doesn't work that well for the second type. Second type is weird. Like, obviously we can't do brute force for the second type. We can for the first type. We're basically like doing some sort of BFS or something at every stage. It's so cold here. I need something for my feet because my circulation sucks too. Woohoo. Life. Alright. So the ith integer is the earliest time step. Yeah, okay. This is really weird. So initially k equals 0. Alright, so type 1 seems like two independent problems. Type 1 seems doable. Type 2 is like weird. That is the idea. Or wait, is it? No, wait, maybe it isn't, because it's sort of like DP anyway, right? How does it work? Is it like binary lifting? Three seconds. Could it be binary lifting? I mean, it's possible. We're basically walking up a tree. Question is, do we need to do that? So basically the idea is we're doing a BFS, sort of. At every point we maintain like a array DP. Where we ask, can we get I somehow? I bananas. Now for the first type, first we round x1 down. No, we round it up. So let like just x equals, or let y equals the rounded version of xi. Then because we do the scaling at every individual step, basically it will go from k to k plus y to k plus 2y, etc. So basically we set dpi is equal to like 1 if dp of I or dp of I minus y or dp of I minus 2y up until dp of I minus, oh, there's a yi, that's annoying, but it's like yi times y, where y again is just this. So if any of these are true, then we still set dp of I to true. And so it's sort of like prefix sums. So that part's fine. Type 2 is a bit more annoying because it's like a tree basically. I guess that's how it works. We're like asking for the, So like every value, when we apply the operation, it will become some other value. Like that. And then maybe there's some other value that also becomes this. And then maybe there's some other value that becomes that. And basically, now here, we're asking for like the entire subtree. Or like the entire subtree within distance k. Or within distance yi. That is a bit harder. I feel like I have solved this problem though. Wait, what's the point of this? K is always an integer, so 10 to the 5th times m. Okay. Good, otherwise it would make no sense. If it was always 1, that'd be dumb. So how do we do the second part? Is there an easier way based on the structure of the problem? We know the tree will have some sort of certain shape. Maybe? Does it? Does it even? Does it? Doesn't seem like it would be an array. We do know parents are monotonic. Like if there's some I and then there's some later index, then that later index will have either a later parent or the same parent. Does that make it? I don't think that makes a difference. They're basically in the realm of any tree. I don't remember. I feel like I have solved this. The ants, like the sum over the subtree with depth at most k. But I don't remember how. Can we do it as like some pre-order traversal? Some sort of like pre-order traversal. How does that work? I don't know why they have the type 1 either. That's just like disrespectful. I don't know. It's not that bad. Could also pre-compute the kth ancestor maybe. Do we need binary lifting? Because that seems like it's going to be too ugly. Like the constant's going to be way too heavy. E is the interactive. Okay. Seems like it's going to be too heavy. is a weird choice of notation, but it just means we do it that many times. I really don't want to do binary lifting. Y is at most M. Yeah. So that's not helpful. Is it some sort of pre-order thing? Oh, I see what we can do. Because we're looking for any value. Okay, so we basically go down the tree, and then whenever we have some DPI, we like mark that like we have this here, and that we have k turns left, so that when we go back up, like now we have k minus 1 turns, and then if we go back up to the parent, then we'll have k minus 2, and for every node we maintain like the maximum number of turns we could ever have left. Okay, that makes sense. And if it's ever less than 0, then it's pointless, right? If it's exactly equal to 0, then that's fine. Okay, cool. That makes sense, actually. Okay, cool. Slightly slow on that, but that's fine. Still doing pretty good. So we basically maintain dp. Okay, so there are no multi-tests, so we can memset everything. In fact, we don't need to memset. Everything's automatically that. Perfect. So dp0 is equal to 1. So for each operation, t, c into t and x and y. So if type 1, then it's easier. And basically what we do is, okay, now memset res 1 size of res. It should be m if res I is greater than 1e7, res I is equal to negative 1. Yeah. Okay, now for cool. That handles everything except for the propagating of the DP. So let's do that. Basically, yeah, memset pref 0 size of pref. Now for j equals 0. Actually, wait. So x is equal to, we take the ceiling of x. So basically x plus 100,000 minus 1. I know it's 99999, just to be clear about what we're doing. We're taking the ceiling so that now we have the actual value that we're going to add by. Yep, okay. Cool. So now we do this. j is less than or equal to m, j plus plus. So pref j mod x plus equals dpj. And so because we're inclusive of everything between I and I minus yi times y, the first thing we exclude is I minus yi plus 1 times y. So it's going to be this. I minus, what will it be? So y plus 1 times x. Note that this value of y is still originally stored in x. That's just how I'm doing it. So it might be easier to call this x. It's just the new value of x where we take the ceiling. And if it's greater than or equal to 0, then we need to exclude it. So pref j mod x minus equals dpx. Then val j is equal to prefix j. And that's it. So we're basically maintaining a prefix sum. We have a bucket for every I mod y, not y, and then we basically update that accordingly. So that's it. That handles the first type. The second type is a bit more annoying, which should be good. Child. We create a vector of children. So first, for each person, or for each guy, we clear it. For each thing, we clear it. So child j dot clear. Now for hello j equals 0, j is equal to m. We compute its parent. So parent of j is equal to, what is it? So it's the ceiling of, so we have a value v, and we set it to, or we have a value k, and we set it to, what is it? So it's k, so it's the ceiling of k times xi over 10 to the 5th, meaning it's, okay, j times x plus 100,000 minus 1 over 100,000. So it's the ceiling. If it's less than or equal to m, otherwise it's pointless. Then child, all right, I don't need the index. Then that parent gets this as a child. Then we run a DFS backwards. Okay, so yeah, all right. So void DFS. And we can also like cache the answers, because why not? Actually, this can be long DFS. So res, if we've already visited, then return the cached answer. This v equals 1. Res v is equal to -1 initially. If we already have the dp value, then res v is equal to the value of y, because that's the number of turns we can have. Now for each child, v res v equals max. We're looking for the maximum lifetime. Then we're going to DFS in x and then subtract 1, because now we go up an edge. Then we return the res. Then we do the same thing, dpi res I is greater than or equal to 0. Could also do val, it's like the same value, but it doesn't even matter. Actually, we do need to do val, because I already have an array called res, so let's not do that and mess everything up. This is val greater than or equal to 0. Note the difference between these are different, so we'll just handle them differently. Cool. Alright, let's make sure this works. So read into n and m, memset res to be 1. This means it's going to be infinity. Basically, it's going to be some huge value. dp of 0 is 1. So now for each thing, everything else is 0. So set this to be that. Take the ceiling value of x. Yeah, because we need to be ceiling because we're rounding up here. Now memset for the prefix, add it to that. It would never exceed m, so that's fine. M is at most 10 to the 5th. Yeah, it would never exceed m. That's good. Then we exclude that one and do some magic. Val j is equal to prefix of j. For I equals 1, I is less than or equal to m, I plus plus, dpi, or equals val I is greater than 0. And if that, then, yeah, let me do the same thing here. This could be I. In total, this is O of nm. This could be 1, it doesn't really matter. So we clear the children of everything. We compute the parent, which is the ceiling of j times x over 10 to the 5th. Then if the parent's valid, make it a child, then do the DFS. So the DFS is if we visit it, return the cached value. Shouldn't strictly be necessary because everything should have only one parent, but you know, just to be safe. Like it shouldn't be necessary at all, but just to be safe. So we set it to -1. If we have a dp value there, it can be y, because that's the number of turns we have left. Then, yeah, then we go over all the children, set it to that, and return it. And then this is greater than or equal to 0. Yep. Then we print the values. Okay. Has some sense. Oh, I should, yeah. Actually, should declare variables. Let's see if it works. Probably doesn't. Can have some hope. Yeah, it doesn't at all. Okay. Whoa, wait, what? So let's see. Cout x. Am I like computing it wrong or something? It should be 3. Oh, nope, don't do that. Should be 3. Yeah, 3, 2, 10, 3. Cout j. Oh, whoops, j mod x. Shouldn't make the most difference. Because we should still, oh wait, no, it would make all the difference. Yeah, okay. That makes sense. Should probably like print a new line. Also, I just realized that here 0 will be the parent of itself. So I should have an extra check and say that if parent is greater than j. Otherwise, it's sort of like messy. We get cycles and stuff. So let's just avoid that entirely. And we'll say, what? Oh, okay. Now we do need j. Yep, because we're having I as a counter, so that's stupid to not do that. Yep. dpj. Yep, and I should have that here too, except this should be greater than or equal to 0. Actually, this should be I plus 1. That's the whole point of doing this. So why am I not doing that? Yeah, that's the whole point of doing it. -1, -1, 1, -1, -1, 1, -1, -1, -1. Wait, what? That's a problem. That is a problem indeed. And the problem is due to the fact that we have this here. What? Oh, J. Idiota. So this should be J. Yep. Am I using J everywhere else? Let me just Control F(I) and make sure. So I plus 1, I plus 1. Everywhere else is J as intended. Yeah, okay. Sure. I hope. Let's not be dumb. That'd be ideal. Alright, -1, -1, 1, -1, -1, -1, 3, -1, 2, 3, -1, -1, 3, -1, -1, -1, 3. Test it here. -1, -1, -1, 1, -1, -1, -1. No, wait, -1, -1, -1, 1. -1, -1, 3, -1, -1, -1, 3, -1, 2, -1, 3, -1. Okay. Do a couple of tiny other tests just to make sure. So the first thing is to test that we're actually doing the range. 1 and 5. We can do like 9. So that's 1. It should be 100,000 and 1. So just to make sure that it only does that. Okay. Now we do that, and then so we do 2, 200,000, and 2. So we can do almost 3 operations. Make sure that works. What? Oh. Yep. We test that as well. Make sure we got rid of the debug prints. Okay, looks good. I hope. That was more of a pain, but I guess we got it, hopefully. So cool. 904 milliseconds. I guess that's fine. Yeah, no reason to be worried. Alright, that was a bit slow once again, but we got it, so can't complain that much. Now we can do E. So we have an interactive. You may use F-flush. Okay. There are n houses. There's exactly one directed row between every pair of houses. So we have a tournament graph. Okay. 2 houses A and B are bi-reachable if they're in a strongly connected component. Oh no. We're going to have to understand SCCs for this. Alright, Dixit wants to buy 2 houses in the city, one for living and one for studying. So he wants to find a pair of bi-reachable houses. And he wants to choose one with the maximum value of Ka minus Kb. Ka is the number of roads. So we have the values of Ki. You cannot ask more queries after the judge answers yes. Wow. That's weird. Okay. That's weird. Well, it's not binary search, so I'm happy about that. Because we know the trend with interactives. What does this mean? I'm a bit scared of this, because this has to do with strongly connected components, and that is not my strongest topic. Haha, yeah. Number of roads leading to the ith house is Ki. So bi-reachable. So if no two houses are bi-reachable, then I guess that basically does it. So we're trying to do like a topological sort or something. So if every vertex has in degree 1, at least one, we know we have at least one strongly connected component. If what? Okay, so something has in degree 0, it's useless. Yes. So if something has in degree 0, it's useless. We can remove an in degree from every other vertex. It's also not possible for more than one vertex to have in degree 0. That's interesting. If more than one vertex has in degree 0, then like that's not possible. So if there's a vertex with in degree 0, then we remove it. And then maybe we have some other vertex with in degree 0, then we can remove that. But at any point in a complete directed graph, there's only one vertex that can have in degree 0. So first we do that process, then we're left with some other vertices that have in degree at least 1. So is it possible that we have like groups of SCCs? I assume we do need some interaction. But why? So now we know we have some set of in degrees, all of which are greater than 1. That's all we know about it. Well, we also know that it's a complete graph. But what does this tell us? So if two things are reachable from each other, what does this give us? Oh, actually, wait. So how does this work? That's sort of a mess. How does this work though? So maybe we have some strongly connected like cycle, right? Then we have some other strongly connected cycle. Maybe it's even topologically sorted. Well, no. Then it is possible that everything from here like every edge from this to this will go down. Like we could topologically sort these strongly connected components. That is a possible thing we can do. And what that means is there's some vertex with like the smallest possible in degree. Oh, and we're trying to maximize it, right? Right. Okay, that is a thing. So the thing with the maximum in degree. If the thing with the maximum in degree can reach the thing with the smallest in degree, what does that imply? Does it necessarily imply that we have a strongly connected component? Like, what if it doesn't? Like, what if we have some weird graph like this? Some deceptive graph like this, and then we have this singular edge from the smallest in degree node in this, or the largest in degree node. Well, it's not an SCC. Wait, hang on. There's something going on here, isn't there? The sum of integers is n minus 1 over 2. If we have this edge, what does it mean? I can't think like this. I can't think in SCCs. That's not how my brain works. Oh, this is annoying. Can I ask the same query twice? Yep. Oh, this is annoying. Wait, so when we have a vertex that doesn't have in degree 0, then everything, yeah, has at least in degree 1. So everything has at least in degree 1. Like, say n equals 5. And we have like 10 edges. So we could have some formulation like 1 and then like 2, 2, 2, 3. So that works. Do we need to query? Do we need to query? That's my question. Do we need to query? I'm kind of suspecting that we don't, but I also don't know. I have this hypothesis. I'm not really sure if it works. So we have n times m minus 1 over 2 edges in total. So say we have x and then everything else is greater than or equal to x. Like, say we had n equals 6, so we had 15, then we could have 1. I don't think it works. No, because we could have something like that. And then that doesn't work. Yeah, okay, wait. Is that possible? So the thing with the largest in degree can reach the thing with the smallest in degree. Does it imply that it's vice versa? Because it's a tournament, right? It is indeed a tournament. So what does that mean for us? What does it mean? No two houses desiring the question exists in this city. Yep. Audio is still working right now, I hope so. There's probably some lag as always. I don't really know what to do about that. It's like we have nothing still but the list of in degrees. Alright, we still have no more information than that. And now we know that every vertex has at least in degree 1, but it could also mean that we have some like induced graph of strongly connected components or something. It's like everything has to be in an SCC at size at least 1. So if we have some structure like this, what does it mean about our degrees? Actually, is it possible to have that? No, because it's a tournament. So every strongly connected component must have an edge with every other strongly connected component. Oh, I see. Right. So we need, for example, this edge, and we need this edge, for example. And we need like that edge. Maybe some of these edges are bidirectional. Right, because it's a tournament. I am forgetting that somehow. So that can exist. So if we have an edge with smaller in degree, or with larger in degree reaching an edge with smaller in degree, or reaching a vertex with smaller in degree, what does it mean? Does it automatically mean they're connected? Can we just do like straight up greedy from that? What does it mean? We could just like submit the guess, but don't really want to do that. Not for div 2s where it doesn't matter. Like I'm going for accuracy here, not blind speed. does this work? How does it work? How does it work? How does it work? How does it work? Is something like that even possible? I mean, it must be, right? I mean, it probably is. Sort of questioning my sanity now. Like 1122, for example. Like, can we have a thing like 1122 where n equals 4? So we could have something like that, and then like this goes here, and this goes here. Now this must have 2 going into it, so this must go here, and this must go here. And this must have 2 going into it, so this can go here, and that can go here. I guess that's 6 edges, yeah. We have something like 0, 1, 2, 2? Or 0... 0, 1, 1... Like for n equals 5. Like 0, 1, 1, 4, 4. Right, so... that has an edge towards everything. That has an edge only in itself. No, we can never have 2 zeros at the same time. Okay, that makes sense. Yep. That does make sense indeed, because they would have an edge between each other and then one of them wouldn't be 0. Right, I forgot my own, like, I proved this, didn't I? Okay, now I'm being dumb. Come on. So some edge with a smaller, some edge with a larger in degree has an edge to a larger out degree. What does it mean? We proved that every edge can reach, every node can reach every other node with a larger in degree. I don't know if we can. Can we? I don't know. Can we? Like inside this component, we know it's an SCC. We could have something with like really huge in degrees, say here. So like everything points into this. And something with like really small in degree here. And then we could accidentally ask that. And of course the answer would be yes, but it can't reach it. But actually every edge in this cycle has to have an in edge to that. No edge from here can go like this. So the in degree of this is at most, if this is cycle size x and this is y, then the in degree of this is at most x minus 1, and this is at least x. So that can't happen. I think it's true. I think it's true. I think because of the way these SCCs are going to unfold, these strongly connected components, like every node can reach every other node with a larger in degree. That makes sense. I don't have a good proof of it. I mean, that's the best proof I have. I mean, It makes sense. Like, I think. And if they're not in different SCCs, then they're in the same SCC. Yeah. So if this has a lower in degree than this, then either it's either it's higher in the DAG of SCCs or it's in the same SCC. Because if it was lower and therefore it can't reach it, then it's not possible. Because we have this constraint here. Whatever this in degree is, this has to be at least that. Right. And everything that dominates this and would add to that in degree would also dominate this. Okay, perfect. Okay, I think that works then. C into N. I'm using B as vis. So if we haven't visited it and its in degree is 0, I can afford to do this, even though it's like so inefficient. I can afford to do this. Then bi is equal to 0 plus count. Can equals 1, break. If not can, break. If count is equal to n, yeah. Otherwise, let's see. So otherwise we can like, yeah, vector pair LL. So we're looking for all pairs now. We're going to sort them by their absolute value. If let B be the one with the smaller in degree. So if B is greater than AC, swap B and C. Then we ask if the larger in degree can reach the smaller in degree. So C out, exclamation. So C has the larger in degree. C into Y. If S is equal to yes. Alright, first we ask question mark. Then we print that pair. And then return. And then, yeah. So, bool comp. Sort them by that. let's see. So here we have a triangle, 3, 1, 1, 1. So we ask for 2, 1. Yes. There we go. 4, 1, 2, 0, 3. Cool. 4, 0, 2, 2, 2. We can ask 3, 2, for example. We get a fully connected graph. Is that possible? Wait. Yeah. Then we get a triangle. So yes. 4. Let's see. 5. Actually, wait. No. 4, 1, 1, 2, 2. So we ask for 2 and 1. Oh, we should sort them in reverse. 4, 1, 1. Yes, okay, good. Now we ask 3, 1. And so this has 2, this has 2, this has 1, this has 1. Of course, we can reach this from this. So we answer no. We ask for 4, 1. So we answer no again. And like, yes. Okay, sure. 7. Yeah. Wait. That is a thing that I should do. Yep. Okay, I'm just gonna look at this over again because I'm making dumb mistakes now. So we set visited to 0, even though we don't actually need to. And then we let the count be 0. So while something, check for each vertex if we haven't visited it, and if it has an in-degree of 0, then decrement everything, set this visited to 1, then add to the count. Then we say can equals 1. This is important. We need to not, yeah. So if not can break, if count is n, do that. Okay. Now for each pair, if we haven't visited either of them, then push it back. Sort by decreasing order of the thing we're trying to maximize, and then assure that B is less than C. Then we ask if C can reach B. If so, the answer is yes. Yeah. Okay. Has some merit to it. Cool. 40 pretests, nice. All right, I guess we go for F now. Christmas game. Alice and Bob are gonna celebrate Christmas. Game theory. Of course, they love game theory. Why would they not have game theory and an F? They just love game theory. Alice and Bob are going to celebrate Christmas by playing a game with a tree of presents. The tree has n nodes. Their AI presents hang from the ith node. Before beginning the game, a special integer k is chosen, where k is very small. Alice begins the game with moves alternating each turn. Any move the current player may choose some node which has depth at least k. And the player picks some positive number of presents hanging from that node. Let's call it m. The player then places these m presents on the kth ancestor. So we pick some presents and we move them up k. Okay. We define some invariant and then compute it. Is that how it normally works? I do love doing that. Game theory is not my strongest suit, so I guess we'll find out how we're doing soon. Did spend a lot of time trying to prove E instead of just guessing it, but I don't like guessing, as at least for div 2s. Maybe when it's a div 1 and it's like Actually, I don't know. It's sort of hard to tell. It's a trade-off between speed and making sure you're actually correct. So of course the depths themselves are independent. We basically get a separate tree for every depth. Although they're not really independent because it's sort of like the way the game works. I've never been interested in game theory. So there's something that's like involved here. This is going to determine my rank, isn't it? Yes, it will. So the way nim works is like we can steal someone's strategy if the XOR sum is 0. Does it work this way too? Is that like the XOR sum of diagonals? Or not diagonals, like the depths. If the XOR sum is 0 in each depth, then like I can steal whatever strategy I want. So if the XOR sum is 0 at each depth, then like I automatically win, I guess. That would be true. Alright, not each depth, like each depth mod k. Or no, not even that. Each depth, yeah. K has to matter. So each time we move it up k. It's not a bad time to learn game theory. I know this is like a thing. It's like a thing here, right? You just read this and then figure stuff out. So nim k is the game representation. Where we have k. Yeah. What is k? So it's the set of all previous nims. Right. Sure, okay. Makes sense. Takes a set and XORs every element with an integer to obtain another set. The mex of C is the mex of A XOR the mex of B. Like 0, 1, and then we... What does this mean? Okay, sure. I can trust it, but like, what does that mean? So it's the mex of the previous mexes. Yep. Sure. I knew that. Don't really know what that means either. So can we solve an individual game and then combine them, I guess? How do we solve like a specific K? Like if we have a particular K, so we're basically solving for like K equals 1 basically, where we have a single tree and then everything we do will move some number of presents up that tree. so we do move stuff up that tree. What happens? Also, the total XOR of like everything is never changed. That is potentially interesting. I don't know what I'm talking about. So yeah, if the max is 0, then yeah, okay, sure. All this is stuff I already knew. I just don't know what to do with it. Just have like a timestamp of learning game theory instead of solving F. That's basically what this is gonna be. It's necessary to consider a simultaneous play of multiple games. Right, so we combine 2 games. It's the XOR of the 2? Oh my god. So that's just like, okay. Proof omitted for brevity, but it can be proven inductively on the value of MT of S. So it's the XOR sum of all of them. Okay. This game name is a multi-set of heaps. Right. So that's where that comes from. So moving it up a tree, what does that mean? So we can XOR the distinct trees together? I guess that's what it means. Although we have to like solve these somehow. Yeah, that's actually simpler than I expected. I don't know why I didn't like think about that for a second. Interesting. I should like look at this tree also. CS Academy. Yeah. Oh, so it's just a line. Alright. Thank you for that sample. That's awesome. So we have O here, 3 here, 2 here, 4 here, and 4 here. So if we start here, then we have 4 and 4. Wait, what? So we have 2 here. No, we have 3 here, 2 here, 4 here, 4 here. So Alice should be able to win. She moves 1 up and then they're the same. And then everything works. So here, yeah. So we have 0244. So here we have O 2, 4, 4. This is not helpful. Let's just draw the tree ourselves. So we have 3, 4, 0, 2, 4. So if the root is here, what can we do? I very much doubt I'm going to figure this out, but we can try. We can attempt to do this game theory problem. It's also the idea of printing things and noticing a pattern. So Alice will move 4 presents from node 4 to node 3. Come on. Okay, I also move these 4. So now we have 6 here. So Bob will move these. Oh, then now Bob can copy or move, I guess. I very much doubt I'm going to figure this out. But it's just like, is there more, or are these just theorems proved earlier, combined position is losing if and only if x are at 0, thus we can just find out pairs of stack sizes. Yeah. Oh my god. Okay, I'm gonna just not read that part. F of t. Yeah, cool. Awesome. Awesome. Absolutely awesome. Awesome. Don't need that at all. Okay. How many solves are on this? I feel like there are gonna be many. Not that many. Okay. How are we doing? Yeah, people have solved this. Sure, implementation. Yep. Okay. I'm going to assume this also involves some sort of like rerouting DP where we somehow exclude the k closest nodes, which is something that's doable, but also not something I trust myself to be able to implement in 18 minutes. So whatever happens, there's no way I'm going to solve this. So maybe I'll try it later just for the sake of like getting into game theory. But for now, I don't think it's worth it to continue. Just because there's so little time left. So I'll leave F as unsolved. And then for the purposes of doing this faster, I'll just push out the rest of the solutions now. Let's just do that. Pretty happy with our rank. Decent speed, not the best, not the worst. How have people done? Yeah, so pretty close to some of the fastest. Some people have interesting scores because of F. Because if you're strong at game theory, you have a huge advantage when you do div 2s. More people have solved E. Wonder if people are guessing it or if it's just actually like... Because I know there is a lot of guessing that goes on. It's sort of interesting. Whoa, wait, did Anton go up or down? Someone like resubmit or something? Oh, he did D last. Right, because it's so like implementy. Okay, well, I'm going to try out this new format now. So, yeah, so for the simpler problems, it's basically going to be the quick and the like the detailed solution at the same time, because there's not much more to cover. So for this one, we're given a number n. We want to find some number x that's greater than or equal to n, so that the GCD of x and the sum of the digits of x, so let like s of x be the sum of x's digits, is greater than 1. And we want to find the smallest x that satisfies this. So the basic idea is, when do x and the sum of digits of x share a factor? So this should possibly recall some theorem that you've probably heard a lot, or some theorem that probably came up in school or something, that if a number y is divisible by 3, then so is its sum of digits. So these two are equivalent. So therefore they will both be divisible by 3 if y is divisible by 3, right? So whenever we get something that's divisible by 3, we're done. We have our number x. And how often do things that are divisible by 3 pop up? Well, we could have, like, if we consider the values mod 3, we have 0, 1, 2, 0, 1, 2. Like, this should be intuitive. We get it within 3 steps, right? So really, if we do the brute force out, it's going to stop within 3 steps, because it's always going to work for any number that's a multiple of 3. So that's basically it. That we can literally just brute force it, and it will stop within at most 3 steps. And the brute force is O of log n. So really that's the complexity, O of log n. In code, that's what this is going to be. We have a function for the computing the sum of digits, and then do that. And then we have this built-in GCD function, which apparently doesn't work for zeros, but that doesn't matter because both of these are going to be greater than 0. So we check if it's greater than 1, then print it. Yeah. Okay. For B, we have some boxes, and we have a big box. We have some small boxes, and we have some big box with a fixed width. So this is width W. And we have some small boxes, each with their own widths, WI, like W1, W2, etc. Where all widths are powers of 2. So 2 to the k for some k, or 2 to the x for some integer x. And it's like a positive power of 2. It's greater than, like, k is greater than or equal to 0. So what we want to do is we want to pack all of these orange boxes into the big one. And to do that packing, we can increase the height of the blue box to however much we need to finish the packing. And we want to find the minimum possible height that we could have, that we could require for the box. And the basic idea is, if you've ever heard of coin change before, the problem of making a certain sum of money using the least possible amount of coins, that works here. And the reason it does is because of the fact that everything is a power of 2. Meaning that suppose we have some... So really, like, all we need to do is greedy. Where we basically say the height's going to be 1. Then we try and pack the first layer we have as much as possible. And so we're going to take as many of the largest possible blocks we have left, and then once we run out of space for that, take as many of the next largest, and then the next largest, and the next largest, and so on. And we do that until either we run out of boxes, in which case we're done, or we run out of space, in which case now we may have to create a new layer, and then we continue on until we run out of boxes. So the greedy is going to work, and the reason ties back to coin change. The basic idea is if you have 2 smaller boxes, or some amount of smaller boxes, and then we have some larger box. So call this weight 1, weight 2, and weight 3. The key idea is that weight 3 is, or like we have some like k smaller boxes that sum to weight 3. The basic idea is that weight 3 is a multiple of these previous ones. So it means that like it's always better to take weight 3 over these smaller boxes, because taking the smaller boxes later on as opposed to now will be easier for us because we'll have like perhaps some smaller spaces in the future to put these in. But it's strictly harder if we don't take weight 3 now, or it's not strictly harder, it's at least as hard, because we may not have another open space of size weight 3. But it's easier to put these weight 1 and weight 2 into smaller spaces than this weight 3, which takes up a larger space. So like following the greedy strategy, it's better to take the larger ones first. Basically, yeah, it is the same idea as coin change, where we're greedily taking like as much as possible. Because having smaller ones later on is better than larger ones. So we take the largest ones first to minimize the number of larger ones and maximize the number of smaller ones. It's not the best proof, but it's existent. Sort of an intuitive proof, I guess. So basically the way I'm doing is I'm keeping a count of each power of 2. Then I iterate over powers of 2, and this basically, it's just some bitwise magic. It divides it by 2 by shifting the bits over 1. And then like while we can take this and while we have at least one of them, then we maintain the count, and then we like say that we took a box, and then while we still have boxes, we keep doing this. And then every time we need a layer, we increment the answer, and then our answer is the number of layers we ended up needing. Okay, so C is a thing. I don't know what kind of thing it is, but it is a thing. So the way this problem works is it's like weird. Basically, like, how do I describe this? We're gonna like send a spaceship through these like lines. Okay, sure, bear with me. So this spaceship has power like 3, for example. Then for every line we touch, it's not realistic, but for every line we touch, we're then going to send a spaceship. We're then going to send a spaceship that notably doesn't touch this line again, but we'll send another spaceship of power 2 out. And then from here, we'll send another spaceship of power 2 out. For every intersection with the power 3 spaceship, we send another spaceship of power 2. So here we send one here, here we send one here, here we send one here. Here we send one here. And yeah. Now for every intersection with the power 2 spaceship, for example, from these 5, we're going to send now a power 1 spaceship in the other direction. So we're going to send 5 spaceships from here in the other direction. So we send 5 of these, and they're power 1. And then when we have a power 1 spaceship, when a power 1 spaceship intersects with a line, we don't create a new spaceship for it. Yeah, so basically the way this is going to work is, and we want to count the number of total spaceships that are ever created and sent. So basically the way this is going to work is follows. If k equals 1, so we're given the number of lines n and the initial power of the spaceship k. So if k equals 1, then the answer just is 1 because no new spaceships are ever created. Otherwise, k is greater than 1. So the spaceship with power k is going to create a new spaceship at each of these. Now each of these points where we have, for example, A1, A2 spaceships at each of these points. For example, when we send all the spaceships here, we're going to send A6 of the spaceships starting from this point, and it's going to create a new spaceship at every point on this interval. So really we're saying, like, we have some array A, and we're going to add A6 to everything on this interval. And then we're also going to add A5 to everything on the interval to the left of this. A5. And we're going to add A4 to this, and A3 to this, and A2 to that. And then A1 gets nothing because all these spaceships just are sent to their deaths. They don't duplicate at all. Sad life. So we're adding on some interval, and then eventually we want to collect those intervals, and then we want to take the overall sums and then use those somehow. So this sounds a bit like prefix sums, doesn't it? We're going to add on some interval, and then we're going to later on like do some stuff with that interval. So basically that is how it works. We're basically going to add on some interval. So for example, from here we can add A6, and then we can subtract A6 here. And then if we let the prefix of I be the sum from j equals 0 to I minus 1 of AI, or AJ, then that's basically going to, every value within this interval will contain the value A6, and then when we're here, it contains the value A6 minus A6, which is 0. So it adds only to that interval. Now an implementation trick you can do is, note that every time we're basically going in the reverse direction. So first we start going this way. Then we know the spaceships are going to be sent this way. So we know that this is going to rely on the sum of every element before it. And this is going to rely on the sum of every element before that, and so on. So what we can really do is we're saying we're taking prefix sums this way. And so the value of this element will be the prefix sum of these elements, or it will be the sum of the elements that come before it. And then once we do that, now we have this new array. Let's call it like B1, B2, B3. Terrible drawings. That's not even a letter. B5 and B6. And then now all these spaceships are going to go this way. So really like, or wait, new color. Now all these spaceships are going to go this way. So the number of spaceships here is the sum of these previous ones, and so on. And then we reverse the array once again. And there we go in the reverse direction once again. And we go in the reverse direction. So really what we can do is, as an implementation trick, we can reverse the array every time. So when we know we're going this way, we can instead say we're going to reverse this entire thing. So that now, instead, we simulate that we're going this way, and that the value here is going to be the sum of the prefix of elements. And then now, because we reversed, now next term we'd be going this way. So we reverse it once again to make it now we're going this way. And then once again, it depends on the sum of the first few elements, or the elements before it. And so that way we don't have to worry about parity or anything like that. So the basic idea is I handle k is equal to 1 like weirdly, so don't worry about that. Just, it's easiest to treat it as a special case. And then you can set, like, in the beginning, you can treat it like we have a single spaceship here, for example, or we have a single spaceship here, and then we're going to send that there. And then at every point, we add to the answer the number of spaceships that are created at this point. Now, then we basically maintain a running prefix sum. Then the number of spaceships that will end up being here is the sum of the previous elements. And then that becomes the new sum here. So we basically set A4 equal to the prefix of that, or the prefix sum of all the previous elements. And then, yeah, and then after that we reverse the array to signify that now we're going in the reverse direction. So that basically settles it. It's just sort of like a bunch of math. It's like dynamic programming in disguise. Yeah. Maybe there's a formula. Like, there probably is, actually. But, I don't really care. I mean, it works. It's O of nk in total, because it takes only k steps to do the simulation every time. So really, we're just, like, efficiently simulating the movement of the spaceships without actually creating all the spaceships. Alright, this one's, like, a pain. Sort of, but also, like, not, but also, like, I'm slow, so maybe. At this point, I'm going to stop reading the statements. So the idea for this is that, yeah, there's not much proof involved here. E is going to have all the proof. The basic idea here is, for the first type of operation, basically, we're going to maintain some values dpi, where dpi equals, can we get the value I? And then, at every step, we recalculate the values dpi. And then at the first point where we have dpi equals 1, or equals true, that's our answer. So given that we can recalculate the values dpi every time, we can figure out what our answer needs to be. So for type 1, basically, if we have some index and we have some previous indices, the value we're going to add, the ceiling of x plus, or k plus x over 10 to the 5th, like, this is constant. So we can really set x equal to the value that we actually end up adding, which is the ceiling of x over 10 to the 5th. Because k is already an integer, so the only thing that matters in the ceiling is x. So we set x to this. So now, from dpi, say like this x equals 2. Then for any like we can go from anything that's like some multiple of 2 away, provided that we take no more than like y steps for it. So like, for example, say x equals 2 and y equals 3. Then if any of these are true, then we can go from that value to this one by doing the operations. So really it's like dp of I is true if any of, like, dp of I minus some jump we can make. So for example, minus some value, let's say, I don't know, c times x, right? So we can pick any value c, and then we say that from this value where we know dpi, where we know the dp value is true, we're going to do the operation c times, and then we'll add c times x, and then end up with I. So we're sort of reversing it. We're saying we can get this value from any of these previous values. Where c has to be between 0 and y. So this is basically like prefix sums, except the problem is that it's sort of weird because we can jump by only multiples of x. But basically the way we can do that is we can break the array up into their values like modulo x. So for example, in one array we'd have 0 and then 2 and then 4 and then 6 and then 8 and then 10. And in the other array we'd have 1 and then 3 and then 5 and then 7 and then 9 and 11 and so on. And we would, if we had x equals like 7, for example, then we would have 7 of these arrays. We would have like 0, 1, 2, 3, 4, 5, 6, and then 7, 8, and then etc. And then now, like, each of these arrays are independent, and every step is a jump of size x. So really now we're just looking for the prefix sum of length y. So that's one way to do it. I sort of do it differently. I keep track of like prefix sums and then like subtract out the elements, and you can have a prefix sum for each remainder modulo x. Basically, any way you do it. As long as you do it efficiently within O of m, then it works. So each transition should be O of 1. You just maintain these prefix sums along these special arrays, and then you can do the transition. Note that this includes DPI already, so if we could have already made it, then we're good. Now the other part is sort of weirder. And in fact, I think actually like, maybe we don't need to do this explicitly. It might actually be easier to just do the same solution for both of them, now that I'm realizing. So maybe that's something that's easier. But basically the idea is with the second part, yeah, it probably is actually easier to just do it the same way both times. With the second part, we can use the formula to figure out, like, for some I, it's going to be mapped to some j. And then this j is going to be mapped to some k. And maybe some other values will be mapped to the same j. And so really what we get is we get like sort of a tree of values that are mapped to other values. And so now for a particular node, say like y equals 2. Then we're interested in, is there any node that is there any node like some previous node like b or something, I'm just choosing random letters, where dp of b is true, and we can get from b, and we're solving for node c, and we can get from b to c in like at most y operations, right? That's the basic idea. So is there a node within depth y where dp of that node is true? And so some idea we can have is basically like, instead of asking that, we basically say for every node where this is true, we sort of like push out the truth to every ancestor to at most, we sort of like push out the truth to all the y ancestors. We're basically like saying, since we can get this, now that we can do these operations, now we can get everything that's within y ancestors of this. And so, so basically, yeah, for every node, we maintain like, it's sort of a different DP value. We maintain the closest node, or the distance to the closest node that's true. So it's like the closest node j where dp of j is true. So for example, on this tree, say this node is true, this node is true, and this node is true. And then y equals 2 or something. Actually, it doesn't even matter. So basically we're saying, my implementation does it a bit differently, I guess. So basically for this, the closest node is itself, so the distance is 0. And also it has to be a child, like we can't, it's directed. So yeah. Then basically this is also 0, and then this doesn't have any child that's true, so it's basically infinity. Then here, both of its children are true, and so the answer is either it's 0 if this node is true, or it's the minimum over its children, and then added 1 because we take another edge. So this distance is 1. Then here, this is also infinity. And then here, this is the minimum. Actually, this one's true, so it would be 0 itself. But if it wasn't true, then it would be the minimum, or be the minimum of these plus 1, which would be 2. So this one's also infinity, and then this distance is also 1, because it's 1 away from a 0 node. So it's basically like dp, where f of I is equal to 0 if dp of I, or 1 plus the minimum of j, the minimum where j is a child of I, of dp of j plus 1, dp of j. And this 1 again is because we take an extra edge. And then basically dpi is true if f of I is less than or equal to y. Like if we have some node that we can get, if we have some node where dp of that node is true, and we can get there in at most y operations, then it means that we can get that value now. So again, these trees are going to be built on the values. And basically every parent relationship is saying that when we do the operation on this, we get this value. So that's the basic idea. Yeah, in code. So again, it's sort of like not necessary to do two separate problems, because really we can build the same tree structure here. It's just a lot simpler, and then we can solve the same problem. Like for example, this has a parent to here, 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 this has a parent to here. And then we do the same thing, and it works. And the reason it works is because we're not looking for like the number. We're looking for simply, do we have any node that it works for? So yeah, that is the way it works. If it were harder, I guess we can do something like small to large or something like that. I guess there's some way to do it that's reasonable. Probably can do it in login or something. In the general case where we're like looking for sum or something like that. But here we read in the value. Here I'm basically doing prefix sums where we take like modulo and then we figure out the one we need to exclude, and then if so we subtract it, and then the value is simply that. Then if we have like any value at all, then dpj should be true, and then we maintain this res array, and at every point if dpj is true, then we could reach it here. So either we reach it here or we reached it earlier. And then here we basically compute the parent and then add that to a tree. Then we do DFS over the tree and we compute this value. And so here what I'm doing is instead I'm saying like we have this value, we set like f of I to be the number of turns we have left of like a valid dp value. So for example, this would be y, this would be y, this would be like, this would be -1, this would be -1, this would be y minus 1 because now we have one turn left. Then this would be y again, this would be -1, this would be y minus 1. And then any value greater than or equal to 0 corresponds to like a valid amount of turns. So it's a similar strategy. And then we just print the answer. E is fun. Yeah, I don't know how to do F, so this is going to be the last one. .5 seconds. Huh, I guess it's like not the fastest because we do a lot of output stuff. Do they test it for a Java and stuff like that? They must have. Okay, so the basic idea is, first, if we have a node with in degree 0, then it means it can reach every other node because we have a tournament. The property of having a tournament is rather important. A tournament being a complete directed graph. So we have every node has an edge to every pair of nodes has some edge from one of the nodes in the pair to the other. So we know that this node can reach every other node. We also know that because of that, no node can reach this node. So this node is completely useless in our consideration. So really what that means is like we should just remove this. And when we remove this, we remove all edges associated with this node. So what that means is that we subtract 1 from the in degree of every other node because we know that this node has an edge to every other node. Every node has an in degree that's like contributed from this node. So now we're left with this remaining graph after we remove this node. So we basically rinse and repeat. If we now once again have a node with in degree 0, then we once again remove that node. And then we continue, and either we're left with no nodes left, or every other node has in degree at least 1. So if we have no nodes, then like automatically there's nothing we can do, because like there's nothing we can do, because there's no pair of nodes that can reach each other. Like we have a topological sort, it's a DAG, so it doesn't work. Otherwise, every node has in degree at least 1. And what that means is we can prove that there's at least one strongly connected component. Now, the conjecture that I will prove in the more detailed version, but in the simple version, it's simply this. If we have, let AI be the in degree of I. If we have some 2 nodes such that AI is less than or equal to AJ, then the big claim is that automatically I can reach j by default. That is guaranteed in this problem. It's I can reach j, right? Yeah. It's guaranteed that I can reach j. So what that means is if we query if j can reach I, where ai is less than or equal to aj, and then we get yes, then because we know I can reach j because ai is less than or equal to aj, automatically we know we're done. We know I can reach j, we know j can reach I, and that's it. So if we query the pairs of I and j in, like, we pick the largest value of ai minus aj first, and then we go in descending order this value. Whenever we get a yes, it means that we found the pair that maximizes this, because we tried all other pairs with the larger value of this and none of them work. So to maximize this, we simply query pairs in descending order of this and check if they work, and if so, then that's our answer, and if not, then we continue going on. So this will maximize this quantity. Right, so I feel like it'd be more interesting if we didn't have interactive and we simply like got told the values, because that way, like, if we have any two equal values, which we must, because the only way it's invalid is if the input is a permutation. So if the input is not a permutation, then we have two equal values, and therefore, without knowing anything about the graph, we can automatically determine that any two equal values have can reach each other, which is kind of cool. That, I feel like that could also be interesting, and the interactive was sort of like contrived, but you know, whatever, it doesn't really matter that much. So yeah, basically we just ask for every pair in decreasing order. Whenever we get a yes, automatically we're done. So for the more details, I'm going to prove this claim. I'm going to prove that ai being less than or equal to aj implies that I is less than j. And the reason this works is because we sort of have to look at the way directed graphs work. So every node has in degree at least one, meaning that we pick some node. Now, we know that we have some node that points into it, meaning that, like, say we pick some starting node, meaning that we have some node that's going to point into it. So let's go to that node now. Now we have some node that's going to point into that. So let's go to that node. Now we have some node that's going to point into that. Now let's go to that node. And etc. And eventually, we're going to hit some node that we've already visited, simply because, like, there are only n nodes. We can't do this infinitely. I mean, we have to eventually get back to some node, right? So say, for example, we have this. So now we have that. So now we found it. So now we have a directed cycle, simply because this process has to stop eventually. We have to eventually get back to some node that we've already seen, right? So if the indegrees are at least one, then automatically we have a cycle. And if we have a cycle, that means we have two nodes that can reach each other. So if all the indegrees are at least one, then we have at least one strongly connected component as well, because every cycle is a strongly connected component. So now, say we have two distinct strongly connected components. That is, say we have a bunch of nodes in this, and these are all strongly connected, and we have a bunch of nodes in this, and these are all strongly connected, but these two components are not strongly connected. And what that means is that, say this node is higher up, then for one of the components, it must be true that every edge between component A and component B, or every edge between a node in A and a node in B, must go from the node in component A to the node in component B. So all four of these nodes and all four of these nodes, all of these edges must go this way. So we have a lot of edges that go this way, right? And we can have many of these components. We could have something like that. We can have some component C. And then because we have a tournament, we know every strongly connected component has to have some relation with some other one. So for example, C could be dominant of A, and C could be dominant of B. And then we can have some component D that's dominated by everything. But we have to have at least one relation between every strongly connected component. Right. Now, suppose we have two nodes in different strongly connected components. So call this node I, call this node J, where I is in A and J is in B, so A will dominate B. Now, what's the integer of I? Well, since A is not dominated by anything, and if it is, then say we have some other like set of components that dominates A, call this like S. Then every node in S will have an edge to A, but it will also have an edge to B because S dominates A, it also dominates B. So really, if we get like some X extra in degree, then that X will be considered in both this and this. So really, we don't have to worry about that. We can just consider the relationship between A and B, or possibly between A and D. Like we could also have some intermediate things that are dominated by A and then that dominate B. But we can't have a cycle because if we did, then they would be in the same strong connected component. So now what we consider is that the integrity of A is at most the size of A minus 1. Because every node in here, well, actually it's size of A minus 2. Because every node in here can have an edge to this, except one of them, because it has to be strongly connected. So we have to be able to get from here to some of these other ones. But minus 1, minus 2, it doesn't really matter. The point is, it's bounded by the size of A. Now, what's the integer of B? Well, because every node in A, by definition of like the strongly connected stuff, every node in A has to have an edge into B. Every node in A has to have an edge into J. So J cannot have an edge from itself to any of the nodes in A. So J has an integer of at least A because every node in A goes into it. So the contribution from the strongly connected component A affects I less than it does J. So J will have more in degree from A. Now, every other component, say it's in between A and B, then it will affect only B. And every component that affects A is also going to affect B because it has to be like a parent. Because if it didn't affect B, then we would have a cycle and then we wouldn't have the structure that we have. Because if we have a cycle, then this component, this huge component where we union A, B, and S is also going to be strongly connected. So it's like sort of like a contradiction. We can think of it like that. So really, what I'm saying is, if we have two strongly connected components, one of which dominates the other. So if A dominates B, then every node in A has a smaller in degree than every node in B. Strictly smaller. So what that means is, now consider some nodes where AI is less than or equal to AJ. Now there are two cases. Either they're both in the same strongly connected component. In that case, by definition, they can automatically reach each other. But otherwise, they're in different strongly connected components. And so because of the way this works, because of the way where we have all of these edges going into here, this property shows that if AI is less than or equal to AJ and they're in different strongly connected components, and also supplemented by the fact that every component has to have a relationship with every other component. Like one of them is going to dominate the other because that's how a tournament works. We have an edge from every node to every other node. So it means that AI is going to be in the dominant component of AJ. Because if it were the other way around, then this wouldn't be possible. AJ would have a smaller in degree than AI, but that's not the case. So yeah, either they're in the same strongly connected component, in which case automatically I can reach J, or they're in different ones and then therefore I is in the dominant one, so I can still reach J. So really that's the proof for this claim, that if you have two values, one of which is less than or equal to the other, then that can reach itself. So, or that I can reach J. So really we just need to find some pair where AJ is greater than or equal to AI and J can reach I. and then this is an I, and then we automatically know these two nodes can reach each other. They're bi-connected. Is that what the word is? They're bi-reachable. Yeah. Bi-connected wouldn't make that much sense. So they're bi-reachable. That's it. And we're basically doing greedy because we want to maximize this. So that's the basic idea with this messy hunk of diagram. That's what's happening. So yeah. That's basically it. So yeah, basically I'm separating the claim from the proof because the proof tends to get very long. So you should be able to see two different timestamps for this, I think, if I remember to do it. Hopefully I will. And that's what's going to happen. Alright, so we got everything. System tests are like almost done at this point. That's pretty cool. Okay, so people did solve. Wrong answer on pretest 18. Wow, that's a pain. Did other people get... Jesus, that's a lot of penalty. Oh my god. Exciting. It's testing. Will it pass is the question. Alright, I'm just drawing this out at this point. I don't have much more to say. I do want to find this out though. Nice. I don't have much more to say, so I guess we're good. Yeah, I don't want to do F. I might figure it out later, but I don't want to do it here because it's game theory and I'm not that good at it. I know nothing about it. I was literally reading the blog on it. So, yeah. That's all I got. Hope you enjoyed this round. Goodbye.